I'm very excited to witness the earthquake this morning. I'm not sure if you know. In Taiwan, around 6:30, there was some little tremor, and I was still in bed, and I felt that the bed was moving away after people. So it's a funny. But so my talk will be slightly different than most of the talks today, but like there'll be a couple of other talks tomorrow, which will be somewhat related. So I'll try to be forward. And of course, having known that the main topic of the workshop will be different, I would have sent another title, but anyhow, it's too late by now. So this is the work in published work and work in progress with people from this list. So Antonio is sitting over here. He will be speaking tomorrow. And this is the story about sort of different ways to understand large-end physics. If we look at through the prism of supersymmetric gauge theories. So we'll, first of all, know that we have a gauge theory with gauge group UN, for example, and then when the number of colors becomes large, then we expect to have some nice vector descriptions, so sort of we can repackage degree of freedom and present the new theory, which is sometimes for most of the cases it's simpler and we can understand this better. And moreover, if the theory is supersymmetric, then there's a hope to solve it exactly. Of course, there are many examples in various dimensions, in 2 and 4, in 3. And so it's meant to be a kind of math talk. So I almost recycled one of the presentations from AMS conference, but I hope I'll be able to explain more details. Similar ideas to work in mathematics. So for example, you make an computation and you have explicit dependence on n somewhere, and then you sort of, you're not interested in this part of the computation, and you just send n to infinity. So you just scale it away and n disappears. And after you've done that, you have sort of different, you have a different answer which represents something else which you'll be able to, which you hope to be able to understand using arithmetic. So there's 3 ways to look at the same phenomena, and I will present some of them today. So there is a nice correspondence between sort of these 3 areas of mathematical physics. So we'll study gauge theories with 8 supercharges in various dimensions, which happens to be the Cyber-Witten solution in infrared, meaning that you can explicitly compute the mass spectrum of its BPS particles. Then there is nice correspondence between those models and the integrable systems. So you have to get some, you have some finite number of degrees of freedom here, and then those degrees of freedom can be thought of as some particles interacting with each other with the integrable potential. And mathematically, it's all described by the sort of newly emergent field of geometric representation theory. So if you haven't heard about this, it's, for example, geometric Langlands correspondence is a part of GRT. And I'll show you some, I'll give some Latin review of what GRT is. And interestingly, that and we'll be looking at large and limit in every corner of this triangle. So in terms of integrable many-body systems, we'll start with some integrable model called Algebra, or it's some integrable model with n particles, and as the number of particles goes to infinity, then you expect to have some continuous description. And indeed it's the case, then you'll arrive to what's called intermediate long-wave hydrodynamical system. Now, this part of the story will go beyond this presentation, so I invite you to read my paper with Antonio. So I'll be talking about this corner and that corner. So here we'll be looking at certain algebra, which is called double affine cake algebra, or DAHA for short, for group JLN. And we'll be studying some stable limits of this algebra. And then when I will become we'll recover what's called elliptic algebra. And then there are some informations. And physically, it will correspond to studying certain BPS quantities in UN 5-dimensional theory with certain defects. And as n becomes infinite, then we'll arrive to U1 theory. So n is gone, so you get rid of it. So it should be present in the final answer, and indeed, you're going to get a different 5-dimensional theory with the U1 PHP. And most remarkably, the larger limits are manifest in the description, and then you can sort of match story here, story there, and so on and so forth. Okay, so let's get started with the lower right corner. This this algebra that I'm describing you how it appears. So the starting point is the space of flat connections on a torus with a puncture. So basically, so you have some principal bundle with gauge group GLN, GLNC, so it's a complex of flat connections. And because the connections are flat, then the modular space is simply parameterized by the equation which is given. So you have the matrices A, B, and C, which are GLNC valued matrices, and they parameterize monodromies around the A cycle of the torus, B cycle of the torus, and the cycle around the puncture. And then there's a condition which relates them together, which is just the fundamental group relation for the torus. So, and then the reason why it's true is because those connections are flat. So this monodromies are just always flat. And we're picking the specific value of the matrix C such that it has a single distinct tagging value. So if T is the non-zero complex number, it's a C star valued parameter, then this is the choice for C. Now, there's an exercise. This space is n-dimensional, complex. The complex dimensional this space is 2n. And whenever we have a complex n-dimensional space, we can always think of it as, well, we can try to think of it as the space of the space of deployment system. So locally it looks like the cotangent bundle to some n-dimensional manifold. If you have some coordinates that live in this M, and then momentum live in the fiber, then you have this nice description of the phase space, and have some nice homomorphic form. And then sort of according to standard dictionary, you can pick some Lagrangian submanifolds inside the space, and upon quantization, they will be promoted to the states in your quantum mechanics. So eventually, we'll decide quantum. So quantization of the space using both mathematically and physically. So physically, it will be quantization of the central group system, and mathematically, it will be information quantization of the modular space of flat connections. And it's when I think about I want to I can vary. I fix it like for when I do the computation, I fix it. And those homomorphic Lagrangians can be you can interpret them by fixing the eigenvalues of either matrix A or matrix B. So let's say A cycle holonomies are fixed, and for B cycle monodromy matrix, but the eigenvalues are fixed. Now, so of course, because there is a nice modular duality on the torus, we can make the change of if you switch A and B and flip the invert matrix C, then the flatness condition turns into itself. And so this suggests that we can sort of double up the problem. So we can take a direct product of two phase spaces, one will just the MA and the other MB, and then we'll study Lagrangian submanifolds inside the whole M space. So, and there are two types of Lagrangians that we can study. We can say take matrix A and then diagonalize it to some eigenvalues alpha 1 through alpha n, and then derive matrix B from just consistency condition that there was in the previous slide from fundamental group relation. Or equivalently, in the other factor, we can diagonalize B and then derive A from that relation. And of course, because of the symmetry, they'll have similar, like this matrix A here will look like matrix B there, and you can switch T to the T or something like that. So there's an exercise, and turns out that there's a very nice change of variables. Well, like as I said, we can indeed say that we can sort of in this frame, when alphas are values of A, and will be coordinates of the integral model, and then to introduce the n new variables, P alpha 1 to P alpha n. And then, interestingly, this matrix A, let's say, yeah, that's right. We can write the matrix A in the second approach as, in the second line here, as a certain lax matrix of an integrable system. I'll say in a second what the integrable system is, but essentially, if betas are the eigenvalues of matrix B, and we just write characteristic polynomial of matrix B, which is just this product of all monomials, assuming that they're all different, and then discuss the gender system. And the characteristic polynomial of matrix B symmetry becomes equal to the characteristic polynomial of matrix A. So that thing would, so this equation, if you expand in powers of u, will generate your integrals of motion for this integrable system. So for example, the first coefficient will be trace of A, so the trace of A will be equal to sum of betas and so on and so forth. Is that clear?
Where are the alpha?
It's a certain, it's a function of both alphas and beta. It's a certain, it's a simple rational function of alphas, e's, and betas. And also relates to one more. Good. So this is the integrable system we're going to be quantizing, and then right. So there's this equation, and then there's the dual when you switch alphas and betas. Now, there's a little bit of math literature here. I'm not gonna. Well, anyhow, so we already discussed information quantization in one of the previous talks, and so if you perform this procedure for our space, the modular space of Gillian connections, and keeping in mind that this is a hyperkähler manifold, then we need to first fix the complex structure where we'll be quantizing this. And sort of in simple terms, it means that we need to fix the symplectic form, and then this holomorphic Lagrangians, they will vanish, such that the symplectic form should vanish from the Lagrangian that we are quantizing. So in fact, if you take p's that from the previous slide and take the symplectic form, so keep in mind that those are star variables. That's why it's sort of, I keep this as a logarithmic variable. And then if you introduce the Planck constant in this exponential with a q, then quantization simply tells you simply replaces the alpha and p alpha. So alpha and p alpha, they q commute. So as you pass q through alpha, then you pick up a factor of q. Right. So good. Now this is called the double affine cake algebra for GLN. I'll give you the relations on the next slide. But what we need for the further development is that the Hamiltonians of the integrable model that we have, the coefficients in the characteristic polynomial of A or B, they form a maximal commutant subalgebra inside this alpha. And if you want to study representations of the full algebra, we just take the representations of the commutant subalgebra and then induce it. Induce the representation for the full algebra. So that will make our life easier. Yes, and then sort of physically what this means is that the space that I have started with this Mn is the moduli space of Wakio in the n equals to h theory. It's called n equals to star in 4 dimensions, and if you take one of the reference compact, so you have three courses one, with h equal to n, and the coordinates of this moduli space are described by vacuum expectation values of BPS line operators that wrap the circle. So if you have, for example, DH group SC2, you have 3 types of line operators. You have Wilson loops with more lines of electric charges, right? You have 2 loops, which are more lines of magnetic charges, and then you have dionic loops. It's like one line of both. So you can have, remember, in this kind of theories, if you allow to have monopoles and dions in infrared. Yeah, and then this A and B will be sort of matrices that aloneness of those electric and magnetic systems. So this is the example. If you take instead of GLN, I'll just take SO2, so I trace out and remove the trace part. So we can parameterize them with this as trace A, trace B, and trace. So X is trace B, trace A, Y is trace B, and Z is trace AB. So you can see that C is not independent. You can derive what trace C is from here. And after work out the algebra, you can find that this Mn is a cubic inside C3. Okay, it's this variety over here, which is for trained I is if t is equal to 1, is called Kelly cubic. It's the C2 orbifold of C star cross C star. So there's this interaction that changes X and Y. Right, it's like S transform that I was talking about. But when t is not equal to 1, right, so then t equals 1 correspond to the identity matrix C, so the puncture, this marked point disappears, and the n equals 2 star theory gets promoted to n equals 4 theory, which is the maximal supersymmetric technique. And most of the features that I'm going to that come along with the right one is not equal to 1, they disappear. So all integrability in the sense that I'm describing will be gone. Right, so then in the information quantization will tell you that x and y will be just, the Q commutator will be this Q minus Q inverse and Z. And you can see that there's nice cumulative limits. When Q goes to 1, everything becomes cumulative. So there's no non-trivial commutation relation between all these generators. And then sort of you cycle them backwards. Right. So these are commutators for Daha and for SO2 Daha. And there's a Casimir operator, which is basically taking this left-hand side of this equation and then sprinkling factor Q in the right place. Ordering is also important. And then it's it's a central element that it commutes with everything, with any of those guys. And the eigenvalue of the Casimir is again some function of Q and T, which is again some deformation of this right-hand side. Good. So very nice physical way to understand why Daha appears in this n equals 2 theory. So we have remember Koroteev R3 process 1, and there is a way to understand how the Q deformation arises in algebra by deforming the space-time itself. It's called omega deformation or omega background in terms of quantum Grassel. And it's basically a certain gravity background which deforms the space-time. So instead of R2, it sort of replaces it by a cigar. So you can think of it as a sort of potential that forces all the fluctuations of the fields to be trapped around the origin of this R2. So basically, and so there is a big price to pay if you want to go, like you need to have a very high energy to go into towards the boundary of this cigar. So you can think of all those field configurations, including instantons, so this is sitting on the tip. And then line operators, they wrap the circle. So the circle is not shown on this picture. And instead we have just single real line. And those operators are just local operators on this real line. And basically they cannot go into the ball. So they have like this vertical direction is direction inside the cigar. So because of this potential, they cannot go into it. And then so as you take two operators and you want to move them around, there is a price to pay, and this price is a Q commutator. How to do that, right? That's right. And then so this is the algebra itself. And if you want to study the representations, then you replace the R by R plus, by a half line, or by an interval. And then you'll study different boundary conditions, which are classified by branes, like Kapustin and Orlov. So when you have a operator approaching the boundary, it will be like this certain string, which is straight between the brane here and the brane at the boundary, and it will provide you a representation for you. Right, so there's many. So, like I said, it was more mathematical talk. This construction allows us to do some mathematical, some nice mathematical. We can generate some nice mathematical results, and one of them is equivariant K theory. Basically, if you're familiar with Gromov-Witten theory and counting on Gromov-Witten invariance, it's a certain deformation of quantum cohomology of the space, which is replaced by quantum K theory, which roughly corresponds to taking your sigma model from the sigma model in 2 dimensions to sigma model in 3 dimensions. So you get an extra circle, and then again, you're studying some intersection theory. So you're studying some stable maps from CP1 to your target, but the way you compute those invariants is slightly different. So it's modified and sort of is called quantum K theory. So what you can tell that the eigenstate, so the quantum Hamiltonians, which are sort of decays, they are coefficients of the characteristic polynomial of matrices A or B in terms of alpha and alpha. After quantization, you can ask what is the spectrum of the Hamiltonians, and you still commute the eigenspace of eigenstates into the same. So it turns out that the eigenstate, this B, is a partition function of a certain gauge theory, which is given by this Kuiper. So it's a one gauge group with two hypermultiplets in 3 dimensions. So it's a theory on R to the process 1. And then the eigenstate will play the role of given tau J function for the equivariant quantum K theory on the potential bundle to this B1. So basically, the Higgs branch of this theory, as well as the Coulomb branch, mentioned that it's the potential bundle to the sphere, the star of B1. And then this construction allows you to do some quantum intersection, some intersection theory in this case. But anyhow, so from the point of view of quantum mechanics, there is a nice interpretation of the eigenstates of those Hamiltonians both in mathematics and in physics. And in physics, this is the what's called vortex partition function of this gauge theory. So in more detail, the Hamiltonians look like this. So the first one, the D1, you have m particles. It's the sort of sum of the shift operators, those p alphas, weighted with the rational function of coordinates and t. And its eigenvalue is just the sum of betas, the monograms of the eigenvalues of the P matrix.
What is the syntactic manifold for this homomorphism theory?
It's this one here. It's a non-compact, right? So you're studying it equivariantly. So with respect to the C-star action, which sort of rotates the fiber. So effectively compactified. Yeah, so that's right. This is the key theory for this space.
So you start with a 4-dimensional bridge theory how to
No, so this is already a 3-dimensional theory. Yes. And then it's a 3-dimensional theory on R2 process 1. If you shrink down this one, you're going to get some 2-dimensional theory. And that's like the key near sigma 1 description of your sigma model. That's grown with the construction. Yes. So that's what makes it a key theory.
So the model space is just Higgs branch of the series?
Yeah, that's right. A Higgs branch of this theory.
Is it T of this?
Yeah, it's T of this. Yeah, so physics, in physics literature is called T of this. Right. Yeah, there are some more theorems. I'm not going to talk about them. There's a classical result by Giventhal and Lee, which allows us to compute the quantum K theory of the flag variety, which is the following thing. It's the oops. We have a C inside C2 inside C3 inside this one inside Cn. So, like, for example, in the projective space, when we look at complex lines inside Cn plus 1, so that would be Cpn, but then instead of generalize the construction by having this consecutive embeddings of complex spaces in one another, so this is called flag variety. Yeah, and then our colleagues from Berkeley and like in Berkeley, so they helped us to compute K theory for that space, and it's given by some generators, which is basically some polynomial algebra of variables modulo the ideal, and the ideal is ideal is given by energies by the Hamiltonians of Toda integrable system, which is different from what we had. And what we had is something more. It's the instead of flag, we have a potential bundle with the flag. So one n is equal to 1, sorry to 2. Then the T star of the 2 flag is just P1. So we get back to the previous example. And in more general, in more generic situation, when you have the n flag, then the equivariant K theory of the space is given by some polynomial algebra generated by alphas, p alphas, t, and betas modulo the relations, which are equations of motion of integrable system that comes from the flat connections. It's called trigonometric Ordinary-Schneider model. And then there's a Demassic limit, which allows you to go from this model and arrive to the product. Right, and it was made possible because of certain proposition that proved that if you take this quiver as a quiver H theory, which is called now T of SEN theory, and study its pooling branch, its space of supersymmetric vacua, then, which is sometimes also called the Kyle ring. So this Kyle ring of this theory is isomorphic to the desired K theory of the black space. Just I'm trying to understand vacua, supersymmetric vacua of the model, and then coincidentally you sort of discover some quantum K theory of those spaces where the single model falls. Okay, I don't have much time yet, but I'm just going to say that there's a nice elliptic generalization of the system when instead of having a rational function of coordinates, you just get some elliptic function. It's rather, again, so you should think of these guys as the C-star value variables. Then what we had before was the trigonometric function, and now it's somewhat into the elliptic function. And interestingly, if you want to study the spectrum of this guy, then there's also nice physical interpretations. We need to take a 5-dimensional theory where this 3D theory sits as a d-head. I'm going to show you in a second what it means, and then it turns out that this partition function is the eigenfunction of the different operators. And the eigenvalue is, again, is the vacuum expectation value of the Wilson line in the Gaussian representation. Mathematically, this is some very smaller picture from the Instanton. It has certain expansion in P is the Instanton counting parameter, and tau is the Kähler parameter on the defect. So if you just have E2 theory with the defect, then there are two capacities which you can expand this. It's the Instanton counting parameter and the radius of CP1. So this counts vortices, this counts Instanton. And Wilson line is again certain variant formula, which I'm not going to explain. But most importantly, there is a series in P. Again, it's the sort of classical distribution, and it was infinite series with Instanton fractions. And then my title suggests that we're going to take some larger limit of those and be able to provide some kind of description. Yes, let's go for large n. And then for simplicity, let's assume that P is equal to 0. Now let's start with a partition with lambda against the flow of number k, which is less than n, or n is the number which is less than n. And then we specify the parameters of the masses of the fields in the Tn theory, or the eigenvalues of the Wilson line, as such that the lambdas of A are columns of the partition lambda, and then T is the T from the modular space. Then for this locus, for every partition lambda, we have that the eigenvalues, those J functions, they get truncated, and instead of being infinite series, they become polynomials. And not just arbitrary polynomials, they are this famous orthogonal system of Magdalena polynomials labeled by partition lambda, and Q and T are parameters. So for example, K is equal to 2, we have two partitions, we have row and we have column. So for example, in terms of explicitly, they now explicitly depend on n. So we have n is equal to 2, we have two variables again. And this is not nice, because if you want to set n to infinity, then it will be hard to keep track of infinite polynomials. But instead, we want to change variables, so we're going to switch from this symmetric functions in tau, in the scalar parameters, to the power symmetric. So after this change of variables, the polynomials they stop depend on n explicitly. They only depend on the partition. However, we sacrifice the symmetry, so they're not symmetric with respect to arguments anymore. And that's just a nice way to construct the Fock space of the new quantum system. So we start with a Fock vacuum, then we simply assign a monomial P to a creation operator with data from this Young diagram, which basically is a string of columns acting on this vacuum. So basically every monomial that we get from the Magdalena polynomial, or equivalently from the Vortex partition function, gets promoted to a state in this new Fock space. So it will be like a Hilbert space of states where the Heisenberg algebra acts. We have creation operators, we have annihilation operators, and because of orthogonality of the Magdalena polynomials, there's a different, they commute to this thing on the right-hand side, which is a certain deformation of the Heisenberg algebra. So you can see that there are two parameters, P and B, instead of just bar on the right. Yeah, so this is the Hilbert space. Now we just need to describe eigenvalues. Okay, I'm going to have to skip through this slide because of lack of time, but somehow time went quicker than I expected. So it's this in the form of free bosons and certain vertex operators. Given some formula, we can show that in this new space there is a correspondence between eigenvalues of those vertex operators and the eigenvalues of the Hamiltonians of my interval system. And then if you write it in this way, then assuming certain analytic properties on T, there's a stable limit when the energy, the eigenvalue of the vertex operator coincides after some factor with the eigenvalue of the interval. Yeah, okay. And then there's nice generalization to case when elliptic parameters turn on. So what's on the other side of the large N transition? So it turns out that this Heisenberg algebra that I showed you before, it's a part of a large algebra which is called elliptic algebra. And mathematicians, so this fellow they've seen it before, and it appeared in the study of U1 Instanton. So it's a certain construction of non-cumulative instantons in 4 dimensions when you have instantons on R4 with 2 invariant parameters, and although they don't exist in sort of classical sense, but in this with non-cumulative deformation, this makes sense to study the modular space. And again, they described by this ADHM construction. You can study this Higgs branch, and Higgs branch will give you the modular space. And our approach allows you to compute some geometric invariants of the space. For example, quantum cohomology, quantum K-theory. Since I'm out of time, we're going to show that it's going to say that the eigenfunctions of the Hamiltonians of the interval system that we have started with, which comes from quantization of Planck connections, it computes quantum multiplication in small quantum cohomology of the instanton modular space. Right. So in fact, and then there's also some nice stable limit from Wilson line operators in the UN theory, and then as you send them to infinity, so we go through some transition such that the remaining contribution also resembles like the Wilson line graph only in this U1 theory. Some 5-dimensional U1 theory, and sort of mathematically describes some differential character for the modular space of instantons on the theory. So there's some nice stable limit. There is interesting duality between various parameters, so that there's 3 parts of the story: interval model here, the ADHM construction after the large N transition, and the integrable system at finite n. And this table shows you that there's no trivial matching of the parameters. Yeah, and this is my last slide. So the double affine Higgs algebra, which we have constructed in the beginning, so it acts faithfully on the equivalent K theory of the flag variety. Right, so that's sort of statement which we derived from the fact that the vortex partition function of the TVM theory is the eigenfunction of those Hamiltonians. So if you can promote this to the statement, and both the algebra and the Hilbert space, they have a nice stable limit. So algebra becomes elliptic algebra, and the space becomes the classical equivalent K theory of the modular space of instantons if you include all the topological sectors. Basically, if you have the K instantons and you hit it with the creation operator, it becomes a sector with K plus 1 instantons, and if you hit it with an annihilation operator, it becomes a sector with K minus 1 instantons. So that's basically what this elliptic algebra is about. And then there's some generalizations of the elliptic deformation, but I'm out of time, so I stop here. It's not it was just an example of where Langlands appears. Like Langlands is part of geometric representation theory. This is another subject, but another example of geometric representation. So like there's some space, you study information quantization, and there's algebra. do the S-duality in 4-dimensional n equals to star theory, that will amount to mirror symmetry in 3 dimensions. And you can relate that to the geometric line.
Any other questions?